Okay, great. This is Dan. Please go ahead. It's being recorded.
All right. So thank you for the kind introduction, and thank you for having me. It's a great pleasure to present our work in data-driven energy systems. So we are in Hong Kong, so we have lots and lots of buildings. Okay, 80% of time people spend indoor. 65% of energy goes to buildings. Among that, half is air conditioning. And even you only count the AC cost of commercial buildings, that's $12.3 billion Hong Kong annually. Right? So I am basically a computer scientist. So what can information and data technology help in this scenario? Okay. So to answer this question, it's always better to see what existing operation and building management is. So current building control and optimization is through strategies based on physical laws. So I give you two examples. So the number one is the thermal comfort of occupants in buildings. So there are many physiology models with equations, okay, so physical models. One notable one is this heat balance model developed by Funger, dating back to 1970s. So it basically says that if your heat generation is greater than your heat loss, then you feel hot, right? And there are equations of how to compute heat generation and how to compute heat loss. Another example is about the efficiency of chillers. So the efficiency of chillers is related to weather data. It's working environment data, working environment parameters, such as working load, and its internal design of efficiency. So there are physical equations on the performance of a chiller. So all these physical laws leads to rule-based control, right? So what is the problem of rule-based control? So it's static and cannot adapt to the changing environment. Just give you one example, like this thermal comfort model. It leads to rules like in Hong Kong, grade A building, the temperature setting, suggested temperature setting is 21.5 degrees Celsius. Grade B building, 22.5 degrees Celsius. And grade C building, 23.5 degrees Celsius. Okay, so here is another example. The rule-based chiller performance is this red line. Okay, the real-time performance is this blue line, blue dots. So you can see that they are quite different. And this red line is quite conservative. In addition to this, so usually chillers at the time of installation, they usually go through a testing period to configure lots and lots of parameters. Okay, but during this test time, still many configurations, many parameters are not tested. And if they are not configured, they won't be used. Right. So all of these rule-based control leads to a very coarse-grained control, and that introduce a lot of waste. So we have done some work. So this first work is a personalized thermal comfort model. This has been done, almost 10 years ago. So we still use the physical model, but we developed a system and we fed them with real-time participatory data. And the result is we can capture the real-time dynamics of thermal sensation of people. Okay, and this leads to a more dynamic temperature setting that results in an improvement in both thermal comfort and also energy saving. For this chiller control, we didn't use the physical equation directly, but we extract features, okay, selected through domain knowledge, and we develop a machine learning model, a clustered multitask learning approach. And using our machine learning model, we can capture the real-time performance of chillers much better. Okay, and this also leads to energy saving. So nowadays, there are many such applications developed, right? Many data-driven applications developed. And our next question is that how can we deploy this application at scale? We are not developing these applications for luxury. Okay, we are not developing only for HSBC headquarters, Bank of China Tower. We want to deploy to 50% of the buildings in Hong Kong, and that's more than 40,000 of buildings. So what is the current situation? Current situation is that the AI application deployment is still a case-by-case effort. Okay, so for example, our project with EMSD, we deploy some chiller control, that's 7 million. If we want to deploy to another building, that's another 12 million project. So there is a vertical coupling of AI service and building systems. So I can give you an analogy. For example, like the mobile phone industry, okay? In the past, like Motorola. Motorola also have like music player, a notepad, some games, driving cars, you know. But those applications are coupled with Motorola phone. Nokia also has its own music player coupled with Nokia phone. Sony Ericsson, same thing. Okay. So what happens now? We have iOS and Android. Okay, and that's separate, basically separate the application development and phone manufacturing. So the major obstacle is that there are heterogeneity in each buildings. And this is why, you know, you have to send field engineer to go to the building to look at the heterogeneity and manage it, and then do something. And then finally you can apply, for example, a chiller control. Hopefully we can develop a platform that can replace these field engineer, automatically hide all this heterogeneity. Okay, then in the future, hopefully that we can just download an application and install. So what are the heterogeneity? Okay, what are the specific heterogeneity? The new things comes from data and AI model. So in this talk, we talk about 3 heterogeneity. Number 1 is the metadata. So this is the naming convention. The name. I give you one example, like this carrier chiller. Okay, so this chiller in this WKGO, West Kowloon General Office of EMSD. Okay. Its name is WKGO basement floor chiller plant number 01. Okay, you need to have this name, and then you can access it for example, flow rate, temperature, power, electricity, and so forth. Okay, but the same chiller at another building, this is Carnegie Mellon, its name is totally different. Okay, this is why, you know, you need to send the field engineer going there and take a look. Well, what does this mean? What does this mean? And if there are local conventions, and if this field engineer needs to go to China to do things, he also needs to understand Chinese. So the second one is the data organization. So the data, all these data storage, they can be different. I give you one example. Okay, like in this database, this is a chiller. Under this chiller, there is a compressor and there is a pump. In a building 2, this is a chiller. There is a compressor. Under this compressor, there's a pump. So the organization of data usually follow a censoring structure, and that differs from building to building. The consequence is that if you develop an application, you not only need to know what data are needed. Okay, I need flow rate, I need chiller power, I need pumps power data. But you also need to know how data can be reached in individual building. And this differs from building to building. Okay. Then you have to write different scripts. So this is number 2. Number 3 is related to AI model, machine learning model. Okay, so we can easily find, in a survey paper like this one, there are more than 100 building load models. Why there are so many building load models? Mostly due to their heterogeneity in building context, background context. So existing models are not effectively used. When there is a new project in a new building, usually people have to develop a new AI model. There is no way to evaluate, how we can use one of the existing model. Right. Then we talk about our recent work on the enabling technologies to handle this heterogeneity. Okay, the first one is on metadata. So one thing to think is that, okay, so different buildings have different local conventions. How about we have a unified standard? Such standard exists. So it's this break standard. So this break standard basically has 2 features. Okay, so number 1, metadata are organized into a graph. This graph is very powerful because you can have the relation between different data. And this is useful for you to search, okay, to retrieve. The second feature is that they are dictionary, okay, basically dictionary developed for both the entities, the equipments, and their relations, okay, defined. So this is not the only standard. There are also other standard, similar ones developed. Right. So after we have this standard, you probably say that, okay, whether that's it. The problem is that if all the building use these standards, this means that we need to have a reset time. For example, January 1st, 2025. Every building change to this standard. If you think that this is very unlikely, then we need converters. Okay, it's just like drivers. Okay, operating system drivers. We need converters. And we find that developing such converter is a cloud game. Okay, so for example, what is this? WKGOBF. This is just some tags. It is a chiller. What are the relationship between this tag, this metadata, and this tag metadata? This chiller plant has location of basement 4. So intrinsically, it is a text processing, right? So we have many NLP, okay. We have many technologies. So one group is information extraction. So it's a task to automatically extract structured information from unstructured text. Just like Michelle Obama is very supportive of her husband, Barack Obama. We want to extract some structured information, some public figures, and their relationship as spouse. So we are very similar, okay? So we want to develop a neural network to process such text. So when you input this text, and then it can output, it is a chiller, a standard. Okay, this is a standard. So in our work, we formulate two problems. Number one is there are some very general equipment in buildings like chiller. So their names is like CP, CHP, CH, CPH, you know, all these. Nobody will name it as Pokemon. And then we develop a neural network model to do the information extraction. Now, some other, you know, metadata are more specific to a building, like this INF. This INF basically is a supply fund. This is very specific to this building. But lucky enough, usually there are specification files, manuals, right? Operation manuals. This is how field engineer, okay? If you send a field engineer, they will read the manual and then they will know, okay, this INF is a supply fund. So basically we develop a reading robots, right? Reading robots to read this specification file, right? And then to output. So there are challenges, for example, like corpus denoise, entity coreference. Entity coreference basically means like Barack Obama and the 44th president of the United States. These two tags point to the same thing, point to the same person. Ambiguity, like George Bush, it can refer to George Bush or George W. Bush, depends on your background context. Right? So I'm going to fast forward, okay, all these solutions, they are in our paper in BuildSys. And then go to the evaluation. So we use 6 building metadata and 2 standards. Okay, so we basically convert these metadata into these 2 standards. Our code is open source. And in both problems, our accuracy is beyond 90%. So basically falls into a practical range. So the second one is data organization. So after you have the standard names, okay, after all the convention, you have standard names, then you can write programs to retrieve data. Right? But as we said that different buildings have different organization. Okay, then you need to write different scripts to reach, okay, to reach the data. The question is that can we extract data in a building agnostic way? And our answer is our anagon system. So in our anagon system has 2 parts. Number 1 is a language, a new language that user or application developer can specify what data are needed. So they only need to specify what data are needed. And we have a query engine, execution engine that based on what data are needed to automatically, you know, extract, automatically go through in different buildings and then extract the data. Right. So first, to develop the programming language, we analyze a large number of applications. We observe that all applications has subsystem. They require subsystems like chillers, lighting, blind. And they need data, they need functionality. Okay, we call it functionality in our paper, like power, set point. And we also define 4 operators: uni, intersection, difference, and join. So with subsystems, their functionalities, and these operators, application developers can basically specify what data they need. And our anagon system will pass this, process this query, and then do automatic extraction, right? And our automatic extraction is based on ontology. I use one example to show it. Okay, so for example, you want to get temperature of chiller and the weather data. So we first extract sub-ontology, okay, sub-segments. And then we go through, okay, these operators. So we define these operators following generic algebra so that they can conform to like associative law, commutative law, and distribution law, so that they don't have ambiguity when you are writing, you know, your program. So we evaluate our system, our anagon system, through both qualitative and quantitative evaluation. So in this qualitative evaluation, you can see that, for example, you want to develop a chiller profiling. Okay, you want to do a chiller profiling application. Then you want to get the temperature data, flow rate data, and power data of a chiller, plus the temperature data of a weather. Then you can just write the query like this. And our anagon can give you the data. And then you feed into your machine learning model. So basically write Python codes. Without anagon, you have to write a much longer program. And for different buildings, you probably need to write different programs. Okay. And we also evaluate quantitatively by lines of code. And we recruit a few developers, and we estimate their development time. So our system can substantially reduce their effort. Okay, the third one is about AI models. So we were saying that many AI models, machine learning models were developed, right? Hundreds of them. Yet they are not effectively used, right? They should, for the machine learning model developed for the same physical system. When I say same physical system, they follow the same physical principles. They should be able to get reused, you know, in one way or another. We tested, okay, a number of machine learning models in different buildings. We can see that some models are good in here and bad in another building. Some models are good here and bad in another one. Okay, so this is rank 1 and rank 4. This is because different buildings do have different contexts. Okay, they do have different contexts, and that causes, you know, the different performance of the models. So how to solve this problem? There are 3 ways. Number 1 is to develop one model for all. You develop a big model. Okay. If a big model doesn't work, you develop a huge model. If a huge model doesn't work, you develop a giant model, right? So recently, I learned quite a number of new English words. For example, this quadrillion. Okay. ChatGPT 5 should have 69 quadrillion parameters. This quadrillion, never heard of this English word before. So this is the first way to do it. One model for all. The second way is currently there are research efforts to develop explainable AI to explain all these models. But that is still a case-by-case effort, right? So we want to choose the third approach is model behavior testing. We want to large, you know, 100 models. There is a target building B. There are 128 models. Which model is better? or we have to redevelop a new one. In many occasions, we probably don't want to maximize our accuracy, maximize energy saving, but we want that the behavioral model can meet expectation. Okay, we hope to find a model out of this 128 that can meet certain expectation. And that's okay. That would be okay. So there are two sub-problems. Number one is what to test. What are the criteria? What are your expectations? Okay, so we discussed this problem in our last year's e-energy paper. But in this talk, I would rather talk about test case generation, right? For target building B, can we generate test cases? Okay, this is a very software engineering term. Can we generate test cases? And in our case, can we generate data augmentation? Can we generate the data that represent target building B? And then we can evaluate 128 models. So data augmentation, okay, to data generation itself is not new. So there are GAN-based models, GAN-based schemes. So GAN-based schemes are good in data augmentation for the same distribution to enrich the data. So if you have seen the distribution, you enrich the data to avoid overfitting AI models. But they are limited in data augmentation for unseen distributions. For example, this target building B, we only have a short data collection period. And we probably also want to add some twist in data generation. So we look into an approach of time series decomposition. Okay, so building data are basically time series data. So in theory, time series data can be decomposed into 4 components. The first is trained. So the living cost is always increasing and our salary remain unchanged. So that's trained. So number 2 is seasonal component, periodic and repeated. The third one is cyclic, periodic, but non-repeated. And the fourth one, reminder component, basically non-random noise. Okay. So we analyze a large number of building data, and we see that in building data, there are seasonal component, cyclic component, and non-random noise. So our methodology is first to decompose, and then augment for each component, and then do a combination, right? So we see that building data has like daily pattern. We do daily pattern by motif discovery. This is a cyclic, and we have seasonal, so basically 4 seasons. Okay. And there are operational cost jittering. So we define 4 types. One is up, one is down, one is up, down, up, one is down, up, down, right? So these are operational cost jitter, like in the early morning, okay, we can see that the chiller has an up, 8 o'clock and up. But in the afternoon, when you start a chiller, there's no such up. And then we can do the augmentation. After we can decompose these, we can do augmentation for each of them individually. Okay. And finally, we combine. After augmentation, we combine this into a new data series. So our evaluation that compared to state-of-art GAN-based schemes, our decomposition scheme is superior in both fidelity and diversity. Okay. Then I'm talking about benchmarking. So we work with this electrical and mechanical services department. This is a Hong Kong government branch on benchmark. When I talk about benchmarking, we talk about to develop some guidelines. Okay, so there are so many smart building, smart city, green city projects, all claim good. How can we compare? If there's some kind of guideline to compare them or validate them. So EMSD has two roles. Number one is operational. So it manages 8,000 properties of Hong Kong government. And number two is policy. So develop some guidelines. So we work with them. Actually, they have developed standards even prior to the break, the break model. So for example, they gave some standards of how do you write access code, how do you write data point codes, how do you write system codes, and so forth. And we advise them to use a graph model. This graph model is more powerful. You know the relation between the data, and then you can easily retrieve, right? And our cloud system can generate this graph for them. Okay, they have the data, and then we can generate this graph. So they're very happy. And the next one is the data extraction platform. So for example, in this West Kowloon General Office, this WKGO building, there are more than 3,000 data files. If you want to do a chiller optimization, and you say that I want flow rate, temperature, and power, these three data, you have to go extract these data from all these files. Currently, this is done manually, okay, by engineer. Well, engineer, they have tools. They have some tools, some of them are visualization tools, but they still need to remember, different data, where it is stored, how is the data organization. And our elegant system can automate this process in a much better way. And we EMSD and us, we developed a competition, model competition event last year. So there are many teams attend, and we give them our system, elegant system, to use, so that they can emphasize on application development. Okay, they don't need to worry about among all these 3,000 files, how can I find this and that data? Okay, so life is actually difficult. People were thinking that life is like this, but actually it's this. So we did some survey afterwards, and they do appreciate such kind of platform. And so after this competition, we have a bunch of models. Some of them are really good. And people ask, can we use these models collected in our future buildings? And my answer to that is that only when you can. Only when we develop some model testing, behavior testing platform. Okay. Because we do see that if you apply a model in another building, for example, if there are many missing values, the performance degrade quite heavily. Okay, not that tolerable. And currently, this is an ongoing project we are working on. Okay, to develop a building AI test platform as a black box, so that we can output the performance in all different in quite a number of criteria, automatic evaluation of models. So as a conclusion, in this talk, we discuss about applications. So there is a transition from physics-based control, decision-making, or I would say decision-making, into information-based decision-making, and that can lead to significant gain. And we talk about platforms to manage AI and AI models at scale. Okay. We handle many heterogeneity. And we also present some of the benchmarking, ongoing benchmarking efforts. And the objective is for cross comparison and validation. So some ongoing work to extension, so from buildings to extend this data heterogeneity and model to energy storage and hopefully EV to make that interoperability in a wider scale. So with that, I would like to stop here. Thank you for listening, and I will be happy to take questions. Thank you.
Thank you very much, Dan. Okay, so we do have quite a bit of time for questions. Any questions from here in live audience? Pedro?
Do you think you can hear me, Dan, or should I come closer?
Yeah, I can hear you.
Cool. Thanks for this talk. I like the decomposition and augmentation because there's very specific like time series that you can kind of decompose and get a lot of more samples by just moving the individual pieces around, right?
Yes.
Why would you only limit yourself to these four? Or I guess you mentioned that cyclical is like a daily pattern and seasonal is like, it's a bit more, there's like a temperature. Did you think about like even more decomposition, or do you feel like this, how much more data does this give you, right? Like you combine four different pieces of information in, I guess, you combine them randomly once you decompose them to get the other samples, or do you do something different? How do you combine and augment that if you can kind of bring more information that way?
I think this is a very good question. So for this type of decomposition work, its objective is to augment or generate better data that can represent, for example, the target building B, right? So you want to find some models for target building B. So there are always rooms that you can improve. There are always rooms, for example, like these four components. So basically three, we cannot find the trained component. So for each individual component, you can do better. Okay, and that also depends on how many data you have from building B. If you don't have any single data like in building B, what you can do is only to use existing building, the average of existing building, right? Because you don't have anything. If you have more data in building B, like 3 months data or even 6 months data, you can do better. You have 2 weeks data, you can do worse. And we agree that for this time series data, there are a lot of work in other domains that people can look into and improve. So there are always ways to improve that you can identify certain new niche. Yeah, that's true.
So in this kind of decomposition, how much augmentation can you kind of extract from this, right? Like if people do augmentations on images, you basically can use each image with each kind of rotation a little bit, and then suddenly you can get, I don't know, 100 times more data, or that's like slightly different versions of it, right? Does this give you kind of same amount, or are you fundamentally limited to just adding a few peaks and troughs here and there, and then that's it? It kind of shifts the particularities about the data, but it doesn't actually generate completely different things.
Okay, so basically in our evaluation, we evaluate like if target building B has 2 weeks data or 3 months data, and then we do augmentation. Like for example, this seasonal component. So our augmentation is basically for example, like from spring, we change to summer. So there is from spring to summer, there is this kind of increase. And for daily pattern is basically, weekly, Monday, Tuesday, we try to add certain, clustering, but the different Mondays are not the same, right? So, and then we do this periodic thing, and we also there are some operational noise. So we put this noise into appropriate places and in some certain appropriate scale. So this is what we do. But certainly we believe, for example, if you have holiday data, currently we don't consider of holiday. If you have holiday data, then if you add like holiday this into consideration, you can do better. Yeah.
Did you think about, so I imagine the problem is when you push this too far, suddenly all of the data that you're training on is fake, and you could actually be completely, so did you ever think about this problem where if you just add too much jitter and combine the patterns more and more and more, you basically generating data which doesn't exist? Is there like, did you ever figure out that there is an upper bound of what augmentation you can do?
Currently no. So yes, your worry is correct. Yeah. So whether we add too many or too little, that's certainly something that's worth looking at. Yeah.
The other,
just one quick question. How do you validate the data you are using in your models?
How do we validate the data used for, you mean for this augmentation?
Yep.
So this augmentation, basically we have the entire of building B, the data of entire 3-year data of building B. Okay, so we only take 2 weeks, 3 months, and then use our augmentation, okay, scheme, and then generate the 3-year to augment to generate the 3-year data, and then compare with the ground truth and see whether we are closer as compared to, you know, these baseline models. So this is what we do.
he already knows the answer. Okay.
Yeah. So we already have, but we hide all the remaining data, and then we use data augmentation and then compare.
I had a question as well, and so I've got a little bit lost on your testing approach. So you're saying there are many different models. We don't know which one is the best. So we need to create a test so that we can choose the best ones or the most robust one. And I think you hinted at the best one may not be the most robust one, but I didn't see the punchline. So what's the, you know, how do you choose which model to use of the 128 that you have?
Oh, okay. So this is a very good question. So what are the, so this is related to what criteria is a good one. What criteria is a good one? That one is kind of really subjective. So we touch this problem of how to define what are the criteria, for example, whether they can tolerate missing data. Okay. So this is a short paper. So it's we discuss about is how to define criteria. And what we are thinking is to do some survey or interview with a field engineer to see what are their top criteria. We believe that their top criteria is still on, you know, safety. So your model don't behave, you know, arbitrarily bad. So even you don't save energy, that's okay, but don't behave, you know, if we have certain missing data, don't behave too bad. So this kind of criteria. But this criteria is kind of subjective. Yes. And then after the criteria we generate, okay, we can do data generation to test whether these criteria can be met.
Okay. The other question I had was about, you know, your focus is heavily on models, but is there so much discussion on model-free control using reinforcement learning as opposed to model-based approaches or model-related control as opposed to standard. What's your view on RL versus MPC?
No, we haven't touched RL because RL is more difficult. It's more difficult to get the ground truth. And RL is from the only my understanding when we talk with building operators, they are more skeptical because they lost more control from RL. In this MPC, actually for our chiller control, we present, early on, that one, they still have an upper, and to be safe, they still have certain rules for safety. These rules are for safety. Okay,
right.
Upper bound and lower bound. Then your data-driven can only work in a range. These rules are for safety. So for MPC, it's very easy. It's easier for them to add these rules.
Right.
Yeah.
I am also very skeptical of RL, mainly because you need a model to train the RL. It's not in the real world. Right. In the real world,
Yes.
it takes too long. So I was just wondering. And then the last thing I want to ask briefly is about, you have a lot of, the first set of results you had were essentially language-based tasks. Have you looked into LLM for these kinds of things? I mean, instead of using these, instead of using the older techniques.
Excuse me, for this language, you mean?
So yeah, instead of using these, your extraction right now, you're using a classifier, NL classifier. Have you looked into the large language model as an alternative to?
Okay. This is a very, very good question. So, actually, after ChatGPT comes out, we immediately tried, but their performance is not good. But my understanding is that if we train them, because this is very domain specific. This is very domain specific. This large model haven't saw this before, but this is an NLP problem. And actually, I think that this is easier than NLP. It's a text processing. It's domain specific is easier than NLP. So if we can train the large language model, that's another path that to try. Yeah, that's certainly true.
Great, thank you. If anybody online has any questions, please you can unmute yourself and ask now. Oh, sorry, there's one more question. Yeah, go ahead.
So your data augmentation on each component, is it achieved by following the physical law or using some physical model? That's the slide. And it all performs like the GAN model. You can start to combine the physical law with the GAN model to do the data augmentation.
Yeah. So whether we add some physical law, so basically this seasonal thing, daily pattern, and you can say that's a physical law, and our jitter. So when we add jitter, so these we analyze operational log, but we simplify them. We only up, down, and then we only talk about the location and the scale. So these are partially you can think is so the physical law as compared to GAN-based model. GAN-based model usually you if there is a totally new distribution, GAN-based model works not that good because it's more automatic. For us, for example, after we have the spring, okay, 3 months data of spring, we know summer is coming. So this is a physical law, right? So summer is coming, and then from other buildings data, we know that the summer extension, for example, in Hong Kong, the jump, okay, the scale of the extension, so that's also physical law. Then this is why, basically why I think the decomposition model can leverage more physical law. But if you have ways to insert those physical laws in GAN-based model, that's also a direction worth trying.
Thank you. Anybody online? Okay, if not, we're actually exactly on time. So thank you very much again, Dan. It was a really very nice talk. And yeah, thank you. Thanks a lot.
Thank you. Thank you for having me.